Okay, here is another example of proving a limit statement. We are going to prove that the limit as x approaches -2 of 7x plus 12 equals -2. Okay, first things first, notice that this is truly the right limit. If you were to do direct substitution, just as a little side check here, plugging in -2 there, -14 plus 12 is actually -2. So yes, this is the right limit, the right value. That's good. None of these proof problems should really be set up with the wrong limit value over here. That would not be provable. So you shouldn't encounter anything like that, and let me know if you do see anything along those lines, because there was probably a typo. Okay, so we need to prove this statement, and using the limit tricks is not a proof. Okay, not a proof. We got to go through our formal process here. We have to start with saying, okay, bring it on, let epsilon be given. Okay, then our limit definition statement says absolute value of f of x minus L is less than epsilon when absolute value of x minus c is less than delta. And I kind of like to keep that off to the side here, personally. That way I can put in my different values so I know what I'm looking for. Okay, now this limit statement gives us a lot that we need for this formal definition. It tells us what f of x is. That's 7x plus 12. It tells us what L is. L is -2. And it tells us what C is. C is also -2. Okay, so x minus c less than delta, my absolute value there, we would have x minus -2 inside our absolute value, which ends up looking like absolute value of x plus 2 is less than delta. Okay, so that's the key statement there that we are going to be looking for in our algebraic manipulations here. Okay, then we're going to start with our f of x minus L statement. Let's put in f of x. And let's put in minus L, -2. And that all is less than epsilon. Okay. Simplify things, combine like terms. You'll see we've got 7x plus 14, absolute value less than epsilon. And we can factor inside the absolute value there. Okay, this kind of shows we're on the right track. All right, let's split that. Absolute value of 7, absolute value of x plus 2. Okay. So 7, absolute value, x plus 2, less than epsilon. And divide on both sides to see our desired statement pop out. Okay, absolute value of x plus 2 is less than epsilon over 7. Notice, absolute value of x plus 2 is less than delta. Absolute value of x plus 2 is less than, and so this is delta, epsilon over 7. So we say, to finish things off, therefore, we want to choose the right delta to go with an epsilon. We want to choose delta equals epsilon over 7. End of proof. All right, so there's that one. Let's do one more here. Okay, slightly different looking function here. We're going to work with a rational function this time. We are going to prove that the limit as x approaches 2 of x squared minus 7x plus 10 over x minus 2 equals negative 3. Okay, now here we know this is going to be the proper limit value. If you want to check it, you certainly can, but remember when you're checking that, if you're using just limit calculation tricks, that again is not a proof, that's just finding the limit. You haven't proved it's the limit until you use this formal definition. So that's what we're going to do. We're going to kick off our proof by saying, give us that epsilon. Let epsilon be given. And we're going to find you a delta based on the information that's given to us. Okay, let's write our limit definition. That's a good place to start. Absolute value of f of x minus L is less than epsilon when absolute value of x minus c is less than delta. And let's see what goes where. All right, here is our function, f of x, rational function. There's our limit value, L is negative 3. And there's our c value that x is approaching, c is 2. Let's put that in. I like to put in the c over here on this side. That way I know the statement that I'm going to be looking for ultimately. So putting in c equals 2, that'd be absolute value of x minus 2 less than delta. So we got to keep an eye out for that. And now let's start our f of x minus L statement manipulations, starting by plugging in the function itself, the function and the limit value. So here's f of x, our rational function. And here is our limit L, negative 3. Okay, that absolute value is less than epsilon. And let's think about manipulating this inside. There's a couple different things that you could do, but probably one of the ones that might spring to mind would be to factor and cancel this rational term there. Okay, or at least factor the numerator, see if the denominator's going to cancel. We'll see about it. All right, so when you factor that, okay, we're going to have x minus 5 and x minus 2. So yeah, I guess I kind of gave you a little spoiler there on accident. It is going to cancel out that x minus 2 factor in the denominator. Well, you would have found out soon enough. Okay, so let's do that. These are going to cancel for us. How nice. Because then we're left with x minus 5 and a plus 3 inside our absolute value. And hey, that actually turns out to be x minus 2 inside our absolute values there, less than epsilon. So hey, we don't even have to divide by anything in this particular example. We have already come to our absolute value of x minus 2 inequality statement here. So absolute value of x minus 2 is less than delta. Here's absolute value of x minus 2 is less than. This must be delta. Okay, so in this case, delta is just going to be the same value as epsilon. Delta and epsilon happen to match in this problem. So we say, therefore, we are going to choose to use that particular delta. Delta equals epsilon. And that will make the formal limit definition hold true. So if someone gave you an epsilon of, say, something very, very tiny, like 1 times 10 to the negative 20th power, that would be them telling you, I want you to get so very close to L along the y direction. 1 times 10 to the negative 20th, that's so, so close. Immediately you can say, okay, I know your delta. I know what you need in the x direction. It needs to be 1 times 10 to the negative 20th as well, because delta should match epsilon for this function, for this limit, according to our formal definition. So that is how we prove limit statements.